In this video lecture, we will find out the equivalent resistance across the diagonal of a cube. So we have given 12 resistors which are connected on the edges of this cube, and we are asked to find out the equivalent resistance between point A and point B. Or simply we can say that we are asked to find out the equivalent resistance across the diagonal of this cube. So for the simplification purposes, I already give names to these nodes, which is C, D, E, F, G and H. And we will be solving this cube by using the rules of symmetry and equipotentials. So now for the simplification purposes, let's consider if the current I is entering at this point A. So the current will be divided equally into three parts, because here we have three resistors available for the current to flow through these three resistors, and these 3 points C, E and H are located at the same distance from point A. So due to the symmetry, we can say that this current will be divided equally through these three resistors. So the current through this resistor will be I divided by 3, and the current through this resistor will also be I divided by 3, and the same current will flow through this resistor. Now at this point, again at node C, there are two choices again available for this current to flow through these two resistors. So due to the symmetry, this current will be divided equally to two parts. So the current through this resistor again will be I divided by 6, and the current through this resistor will be I divided by 6 also. And at point E, here also we have two choices available for this current to flow through these two resistors, and this current will be divided equally due to the symmetry. So the current through this resistor will be I divided by 6, and the current through this resistor will also be I divided by 6. And same is the case for this node H. The current will be divided equally due to the symmetry. So the current through this resistor will be I divided by 6, and the current through this resistor will also be I divided by 6. So now at the point D, these two currents I divided by 6 and I divided by 6 will meet up again and make a current I divided by 3. And at this node also, at node F, this current I divided by 6 and this current I divided by 6 will meet up again and make the current I divided by 3. And at this node, at node G also, this current and this current will meet up and again make the current I divided by 3. So now at point B, these three currents will make the current I, and this current I is basically the same current which is entering at the point A. So we can say that there exists symmetry in this cube. So this network is available in the three-dimensional. Now to understand this analysis more easily, let's transform this network into two-dimensional. So for that, let's consider if we have this point which represents the point A, and the current I is entering to this point A. So at this point A, the current is divided into three paths. The first path is this one from A to C, and the second path is this one from A to E, and the third path is this one from A towards H. So again the current is divided into three paths. The first path is from A towards C, and the second path is from A towards E, and the third path which is followed by this current is from A towards H. Now at this point C, the current is again divided into two paths. The one path is from C to D and the other path is from C to F. So the first path is from C to D, and the other path is from C to F. Now at this point E, the current is again divided into two paths. The one path is from E to D and the other path is from E to G. The first path is from E towards D, and the second path is from E towards G. Now at this point H, the current is again divided into two paths. The first path is from H to F and the second path is from H to G. The first path is from H towards F, and the second path is from H towards G, This is G and this is F. So now from this you can easily see that these 2 points are the same points, these 2 points are the same points, and these 2 points are the same points. So now let's join these points. These 2 points are the same because this is point D and this is also point D. And these 2 points, F and F, are also the same 2 points. And this point G and this point G are also the same 2 points. So finally this is point D, this is point F, and this is point G. So finally this point D is connected to this point B, and this point F is connected to point B, and this point G is also connected to point B. So these 3 points is finally connected to point B. These 3 points is finally connected to point B. So let's say this is the point B. So now this is the 2D version of this 3D problem. So now by using the rules of symmetry you can see that these 3 points are at the equipotential points, and these 3 points are also the equipotential points because these 3 resistors are at the same distance from point B, and these 3 resistors are also at the same distance from point A, because this resistor is 2 resistors away from this point A, and this resistor is also 2 resistors away from this point A, and this resistor also. So these 3 resistors are at the same distance from point B, and these 3 resistors are also at the same distance from point A, and the same is the case for these 3 resistors. So from this we can say that here we have an equipotential at these 3 points and an equipotential at these 3 points. We can replace these 3 points by a single point and these 3 points by a single point. So let's redraw this network again. So now let's say this is the point A, and this is the point CEH. This is the point CEH. And this is the point DFG, and G, and this is the point B. So in between point A and CEH we have 3 resistors connected. Now in between point CEH and DFG we have 6 resistors connected. Now in between DFG and B we have again 3 resistors connected. So now this is basically the simplified version of this 3D network. So now we can use the rules of a series circuits and parallel circuits to find out the equivalent resistance between point A and point B. So now if you analyze this network, then you will see that these 3 resistors are in parallel, and these 6 resistors are also in parallel, and these 3 resistors are in parallel. So the equivalent of these 3 resistors is, let's say, 1 divided by RA is equals to 1 divided by R plus 1 divided by R plus 1 divided by R. So RA from this equation will be equals to R divided by 3. And for these 6 resistors, let's say 1 divided by RB is the equivalent resistance of these 6 resistors, which is equals to 1 divided by R plus 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 1 divided by R. So the equivalent of these 6 resistors RB from this will be equals to R divided by 6. So now let's replace these 3 resistors and these 6 resistors and again these 3 resistors by its equivalent resistance. So let's say this is point A. So the equivalent of these three resistors is R divided by 3. And the equivalent of these 6 resistors is R divided by 6. And the equivalent of these 3 resistors is R divided by 3. So now you can see that these 3 resistors are connected in series. So the equivalent resistance of these 3 resistors is, let's say, RAB is equals to R divided by 3 plus R divided by 6 plus R divided by 3. So the equivalent resistance of these 3 resistors is equals to 5R divided by 6. So the equivalent resistance between point A and B across the diagonal of this cube is equals to 5 divided by 6 into R. So this is basically the equivalent resistance across the diagonal of this cube. So it's all for today's presentation. If you have any doubt, ask in the comment section. See you in the next one.